And so the way Bernstein writes it is this. He writes it like this. Let us see better what this means. Okay, so I can erase this because this will. So the first thing is that this operation is perceived not on the Cartesian product but on the tensor product. And this is not a big deal because we all know what tensor product is. Because instead of saying it's a bilinear operation, it's a linear operation. It's not a big deal. So whether we put on this thing or not, it doesn't matter. What is this saying? It says that so it says this. So because you remember CGG was the
YX.
YX, yes, of course. So is the one exchanging the X with the Y. Okay. But it's interesting because the way you write it like this. See, this is the same way of writing it also for the regular vector space, where you take for CGG the one sending xy to yx.
You should just add the minus sign.
Huh?
You should add the minus sign.
Minus, yes. Of course, I forget. Of course, it's a minus. See, this is the errors. See, I didn't write it because it's obvious. Now, anti-symmetry says that xy is minus yx, right? So here we add an extra minus. So when x and y are both odd, xy is yx. Okay. So, but what I wanted to point out, I'm sorry because of this stupid error, take the attention away. What is really important is that the CGG, depending on how you choose this will become the regular anti-symmetry for superalgebras. Because if you choose CGG, so here you could take this. So if you choose this becomes the anti-symmetry as we know it. The one that Fabrizio is lecturing about. But if we choose the one with the minus, this becomes the super one. See the trick. What is the advantage of doing this? Is that if you look like this, if you do like this, then it becomes you can transfer many properties because they're all hidden in here if you do this game. But I think it's also a more fundamental way to see this.
You can say this is like a Lie object. In any
It's a Lie object. Yeah, I didn't want to say the word category in this class.
Okay.
I'm making an effort.
Okay.
Stephen enjoys speaking about categories, but no, non c'è niente. No, hai ragione. Marta, you can always ask me questions, and as you can see, I can make stupid errors that make the audience feel comfortable in asking me questions. I do it for that, of course. So the Jacobi identity, so it says that if you take So if you take the product of three things, and we compose it with this L and with this sigma. And of course, as I'm used to, sigma is a permutation. Now let's try to be good. Let's not do like this. Because I usually forget to write the action, but no, this time I should be good for a while at least. So it's so what I have to specify sigma. So sigma is the permutation. So right. How do I write? It's the permutation sending 1 to 3 to 1 and 3 to 2. And we want this to be 0. Okay. Now let us see what is the result. This thing.
Just out of curiosity, the fact that the exclude characteristic is for this?
Yes, of course. The characteristic 2 is for the anti-symmetry, because when the two things are odd, if the characteristic is 2, see xy is equal to yx, so you get 2 times xy, you get 0, and the 3. But we will see more later when we do the calculation, it will become 0. There is a way to solve this, but I don't remember the definition. It's not hard. Okay, what is this L sigma doing? So L sigma so sigma takes a U times V times W takes to -1. So it is times U times V. And here I should put okay, we should put the parity. So we exchange V with U, and we exchange W with U. So you have to put parity of U, parity of W, parity of U. Okay, so this is the rule. And what if we apply again L sigma? So if we apply again, we get so it's better to compute L squared sigma. So this is U times V times W. Because we know it is the same. So 1 was 3. No. Why didn't you stop me? That's not right. I should have done sigma -1, right? Not the sigma here. But the sigma, okay. It's okay. Because, so I should have done sigma -1, but sigma -1 is sigma squared. So this is really, this is sigma squared and this is L sigma. I'm a disaster. You see the point, Martha?
Yes.
Yeah, it's disastrous. So it's, okay. So I'm doing the square, so I should send V here. So this goes, no, let me do this. Now I'm very confused. So this should, no. I did the right here, but I can't do it like this.
Well, it's,
I'm
given the way you define, right, it's, the first one is the actual valid sigma, right, because it's sigma inverse, but applied.
No, okay. The only way I can do this is this. So I have to write V1, I'm sorry, V2, V3. I'm not good in permutations, calculation. So if I do this, so this is U, V, W, I'm sorry, so I just can't do it. So this is V sigma minus 1, 1. So the sigma minus 1 sends 1 to 2, hopefully, 2 to 3, and 3 to 1. This is the only way I can do it. So this is V2, V3, and V1. So this is sigma minus 1. I'm sorry, Fabrizio is sitting here getting very discouraged. And then is, now if I apply again sigma minus 1, so 2 in 3, no, yes, because I apply to the index, right, not to the position, that is the confusion. 3 in 1. Now then I put the sign, and this is 2. Am I doing this right? Hopefully. Now the sign, so the sign is, so this is, okay, so, let me write this, so this is V times W times U, this is W times U times V, hopefully. And the sign, so here I'm exchanging so I'm sorry, this is, I made a mistake and then the things didn't go well. And here, so of course I have the same thing, and I also have to multiply by what has been exchanged, which is VW plus U and V. After this little calculation,
This is a sigma.
this is all L sigma, yes. Because my habit is to forget the action. This is what I do, I don't have the action. But let me try. Okay. No, but I know what it should come out, so we can.
So the first one is right. So the first one should be right.
The problem is that after I made the first mistake, then I could not recover anymore between -1 and sigma, so I had to redo it like this. Okay, so this should be that formula. This one, Jacobi should say U, V, W plus, then I have the L sigma, which is -1 U, W plus V, U, V, W, U, plus -1, except that instead of writing all of these things, you can write this is all the same, but you can just check things here, from here to here, right, to get the sign, because it's the same. We just proved this is an action. So we could write the things that are reversed here, which is U, W is reversed, and then that plus, if you write the whole thing, it will come the same. So W, U, V equals 0. And this is the Jacobi identity. And the whole point that is making Bernstein is that if you write like this, and if you take a sigma as the usual action of the permutation, it's the Jacobi identity. It's not this twisted thing. So it's all right. Let us see an example of a superalgebra. I'm going too slow. So the matrix superalgebra. So let us look at the super vector space. This and we're looking at the morphisms from this KMN to KMN. Now, the fact that we write it like that, it shouldn't make worries, because this is nothing like this, right? So it's a vector space of dimension m plus n, where we fix as the basis, this basis, right? E1, em, epsilon 1, epsilon n, and usually the Latin letters are for the even part and the Greek one for the odd. Now, notice that let's do an example, because it's really very stupid what I'm going to say. So, phi corresponds to a matrix. So if you have a K2 from K2. But what happens that if I say, okay, what are the matrices that preserve the parity? If you want to preserve the parity, this should be 0. Because, see, every time you have a B, you're sending an even element into an even plus an odd one. So this preserves parity. And if you take some phi, which is this one reverses the parity, because takes an odd element and sends to even one. So this suggests that we write so the set of all endomorphisms of supervector space, I let you prove this, but it's straightforward, is the parity preserving plus the parity reversing. So this is parity preserving. And are all matrices of this type. And these are the parity reversing that all be of this type. So we decomposed, this becomes a super vector space itself. And in order to make it a D superalgebra, we need to define bracket. So a bracket of two matrices, by definition. So we know that the bracket of two matrices in the classical, in the ordinary setting, will be matrix X times Y, and then you do minus Y times X, except that here the parity will, so it's X, Y, minus. Here you have to be careful, as usual, that generic matrix, if you write matrix A, B, C, D, which is of, you see, M, and so it's a block matrix, right? this, I was doing the 2 by 2 case, but the general case is the same. If you have this definition, it will not make sense for the generic matrix because it's not even or odd, it's mixed. But you can split this as and then you can apply this definition. I'm saying, what I'm trying to say is that this is not defined for all matrices. It's defined for homogeneous one, but the homogeneous one will make, by linearity, you give all the rest of the matrices. Okay? Because you split like this and you make the multiplication. And I leave you as an exercise to verify that this definition actually works. So this will give, so verifying is immediate, I mean it's, okay. Now, all the Lie superalgebras that we'll be interested in for this seminar will be inside this matrix algebra. They don't have to be inside. I mean, it's possible to have something which is very interesting that is not in here. And I will try to give examples later on. But what I want to do, so the plan of, since I give the definition now I feel comfortable to speak about the future, I want to first discuss some foundational things like this one, which I don't know if you're happy with, that's probably boring, I don't know. I want to understand the foundations for another time. Then I want to go into definition of classical superalgebra, and classical Lie superalgebras will be inside the matrix algebra, and they will be equivalent of the classical Lie algebra of families A, B, C, D that you have classified, right? Classical symbol. And we will not classify because they're much harder to classify. But at least I will try to give a feeling on what is the deal with the classification, what is the deal with the construction. And then, hopefully before Christmas, I want to do something about representations, which is what I'm interested in mostly. This is the plan. But for now, I won't stay on I will stay on the foundations for now. Okay, so let me, I want to make an observation on definition of Lie superalgebra. And the observation I want to make is the following. So I have this bracket which has the two properties, the anti-symmetry and the Jacobi. But there are some very simple but yet very important observations to make. The first observation is that I forgot to say important thing, which is obvious to me, but it's not obvious to you. So this map should be parity preserving. I forget to say. This is a parity preserving map. Sorry. All the maps are parity preserving, and those no, but I will explain in what sense those are also later on. I forgot to say in the definition. Very shameful that I forgot. Yes?
All the morphisms you consider between the supervector spaces are parity preserving.
The answer is no, because here is not a parity preserving, this is parity reversing. Okay? But in general, yes. But here, no. So it is particularly shameful that I didn't say parity preserving there, because that is very important. In the definition of the superalgebra, the bracket is parity preserving. Steven, why didn't you stop me?
Sorry. I mean, it's,
It is so obvious that it must be parity percent.
The
Yes.
category of connector spaces is with parity percent.
I don't want to express
Yeah.
myself.
there's.
No,
it's-
no, don't say,
that's
don't
too-
say,
Too complicated.
don't say, it is too
It's
complicated.
too complicated.
But the philosophy should be yes. But here, evidently, if you insist to have a parity preserving, you get a very stupid theory, because then here you get just a block, right? You get first block and second block. You don't get all the matrix. You see the problem? Okay. This problem has a solution which I don't want to say. But I said these are parity preserving in some sense, but I don't want to say which sense. So okay, I'm making a mess. So, once I clarify this very bad mistake that is recorded forever, I feel so bad.
But what do you mean by parity percentage for the product?
I will say in a moment. Okay. No, it is clear what I mean, because G times G, it's, no, parity preserving is clear.
It's a different meaning with respect to.
No, it's the same. This is G0 times G0 plus G1 times G1. And then we have G. Okay, this thing I said at the beginning.
Yes.
No, but it's very good that you're asking, because we're doing all these new things. There could be some confusion. Okay? So this means that this goes inside the G0 and this goes inside the G1. It's very important, this one. So the observation I want to make on this, at least I want to make this observation, is that no, it's my fault, because for me it's obvious, it's parity preserving, but one must say. So the observation I want to make is that since this bracket is parity preserving, this definition tells you that G0 is itself a Lie algebra. Because the bracket, when you restrict to G0 times G0, this is forced to send this. So where it is, what do I want to say? So it is, no, actually it should go to this, times this.
No,
Huh?
no, if
No,
you restrict to this, it goes to G0. We are restricted.
I'm confused now.
The bracket goes from G tensor G to G. So
Yes. One of these obvious things is just very upsetting. So this goes to G0. Okay. So this implies that G0 is a Lie algebra. And this is a very important fact that we use all the time. Okay. Second thing, I have class. There, I have to go now. So the second thing is that G1, the odd part, is G0 modulo. What does this mean? That if I have a bracket, or so if I have G0 times G1, this is forced to go to G1. So, and one can check that this is the property of a modular map. You have to check, but it's true. So this is, maybe next time I will say more. Okay, so, other thing, so we have also this, and this map is symmetric, which means that the image of xy is the same as the image of yx, because that's a bracket, right? So x times y goes to xy, but also y times x goes to xy. I'm just reasoning on the properties of the bracket. No, you don't see, Martha?
No, but okay.
No, because This should go to the bracket of yx, but the bracket of yx of odd element is symmetric. It's the definition. Very natural question is that suppose I have a G0 module with this property. So I have the algebra, I have a G0 module, I have this property. What is missing to have a superalgebra? Yes, but what is equivalent to Jacobi then? Is there a condition I can check to ensure Jacobi? There is, it's called the cubic condition. So this, next time I'll prove this. So this 3 gives Lie superalgebra. If I ask that x it's called the cubic condition. Because a situation where you have a G0 module is it's very, what can I say? It's a very natural question, say how much the bracket is determined by these 3 things. And the truth is that it's not determined by these 3 things. You need the extra thing. Sorry, I don't know, it was probably very boring to people that know already this thing, but next time it'll be less boring, because there is something I cannot do, so you will help me.
So you will let us know when next time is.
I think it will be this time, because speak with parlate con quegli altri. Sentite la vera, come posso dire, la vera volontà. Sì, ma anche capisco che uno non lo firmi a scatola chiusa, però se uno fa spostare l'orario e poi non viene, non lo so. Cercate di fargli capire questo.